Just to recap, gas takes up as much volume as you'll give it, and the particles zip around at a higher speed generally, kinetic molecular theory wise. Solid, the particles are more packed together. They don't take up whatever volume you give. It doesn't expand. Well, it does, I guess, when it heats a little bit. You do get heat expansion, but it's not free to move. And with a liquid, it's free to take on any shape, but it generally doesn't take up more volume. And yes, I know, again, you do get a little bit of heat expansion, but not a ton more volume. Okay, let's take a look at this next bit. This idea of the graph stair-step model. So describing the energy for something as it transitions from one state, or sometimes people call it the next phase. I'm going to add in some information here. And I want to stick with the idea that I'm talking about water because it's very relatable and because we're mostly made of water. So it makes sense to stick with water. So I'm going to stick with minus 20 degrees. Oh, and I should have temperature in degrees Celsius. I'm not being terribly formal about this graph, but I'm going to go from 20 to 0 to, we'll call it pure water, goes up to 100 degrees Celsius. And then I'm going to top out again, just like my previous graph, at 130 degrees Celsius. And as the energy increases, we're talking about the heat energy measured in joules as we transition across this thing. I want to focus not on the steps, but on the actual transitions, the phase transitions. So the fusion energy and the vaporization energy. I'm going to put a little bit of writing in here. First, the heat energy appears, I'll just underline the word appears, to do nothing. During EF and EV. And the reason it appears to do nothing is due to the fact that zero temperature change occurs. Of course, something is happening. The particles are getting vibrated faster and faster. So we can say really, as opposed to what it appears to do, the energy is being used to break down intermolecular connections. Cohesion. So that's what's actually happening. Even though it's not raising in temperature, those connections between particles are breaking down as you shake harder, harder, harder. However, when you're cooling down, when cooling down, this energy is released to the environment. And when that happens, we calculate it to be negative. In other words, energy loss is a negative energy. Now, if I want to zero in on latent heat of fusion, I've just called it fusion so far. We got a name for this, the latent heat of fusion. This is the amount of energy required to, and I'm going to use this word, to just, underline, to just change 1 kilogram of a substance from a solid to a liquid. So in other words, we're not trying to change the temperature. All we're doing is achieving a change of state. Okay? So with no temperature change at all, just a change of state. Just achieving liquefaction. Now I'm just going to give this equation to you as a freebie. We're saying that this fusion energy is equal to a new coefficient, LF. This is the latent heat of fusion times the mass of the object or the material that's being liquefied. So I'll just throw this out there that LF is the latent heat of fusion. And it has units of joules per kilogram. Notice that it's not joules per kilogram degree Celsius like heat capacity. Specific heat capacity is joules per kilogram degree Celsius because we're not trying to change its temperature. All we're trying to do is melt it. So it's joules per kilogram to just melt it, not change its temperature, just melt it. Okay, so the units actually kind of tell the story in this case about what's actually going on. Now, latent heat of vaporization, very similar. I'll write the whole thing out, but I could say it's the same thing except for going from liquid to gas. So the amount of energy required to just, again, I'll underline and put it in red because I really want to emphasize that we're just changing 1 kilogram of a substance from a liquid to a gas. No temperature change. So same thing, but from liquid to gas. And the formula actually looks really, really similar as well. It's EV is equal to LV times M. And again, LV is latent heat of vaporization. Okay.
LV is for Lord Voldemort.
What's that?
LV is for Lord Voldemort.
It is not for Lord Voldemort. No, we should not speak of him. But the units are also joules per kilogram. Okay. Notice there's no change in temperature or anything like that. We're just talking about changing it from one state to another, one phase to another, depending on who you're talking to. So a phase change or a state change, those are synonymous things for us. Okay. All right. So I want to take a look at an example here. Zoom out so I can capture the whole thing. I want to take a look at a latent heat of fusion for some mystery substance. I don't even know what this mystery substance is. What's the latent heat of fusion for a mystery substance? So I'll underline latent heat of fusion so I know what I'm dealing with a mass of 0.55 kilograms that requires 9.56 times 10 to the power of 4 joules to melt it with no change in temperature. In other words, all I got to do is transition this part of the graph between my two fingers, right? If this is my visual for this. So I look at my equation, I say, okay, well, if I want to figure out the latent heat of fusion, I'm looking for the LF value. So EF is equal to LF over M, or LFM. LF isolated is equal to EF over M. In my givens, it looks like I have an EF of 9.56 times 10 to the power of 4 joules. Sorry, I didn't block that off very well. And then the mass is 0.55 kilograms. And so when I go to sub in my values, this is actually not that hard to deal with. I end up getting 9.56 times 10 to the power of 4 joules divided by the mass, 0.55 kilograms. And I get a big number. I get like 173,000-ish. Does that sound right to people? Yeah? 173,818.18 joules to be exact. Oh shoot, my units are messed up and nobody even called me on it. The units for this guy should have been joules. Oh no, that's right, joules. My units are good. Joules per kilogram is the units that I was going for LF. All good. And then to 3 sig figs, because I think that, oh no, 2 sig figs, oh by golly, is 1.7 times 10 to the power of 1, 2, 3, 4, 5 joules per kilogram. Okay. And people say, well, okay, well, that's all well and good. Does that mean that that mystery substance always has that latent heat of fusion value? Yes, that's what that means. That means that the latent heat of fusion value is a constant for a particular material. So like water has its own latent heat of fusion. If I were to melt down iron because I'm working in a smelting plant or something like that, iron would have its own latent heat of fusion. All these materials have their own latent heat of fusions. And likewise, all these materials have their own latent heat of vaporizations, the LV value. Like this is something that's specific to that material. And that's something that a metallurgist or a chemist or a cook or whatever, somebody who's like a food scientist might care about. And here I've got a little mention here, LVW. What do you think that's the latent heat of vaporization for? Water, right? That makes sense in the context of what we're doing. Latent heat of vaporization for water. So here I've got a glass of water. I can label it W for water if it helps, but you don't have to. I got a glass of water on a sunny window and it was left to evaporate. The water has a mass of 200 grams and a latent heat of vaporization of such. How much energy does it take to evaporate the glass of water? Now, when I say evaporate, I mean just take it from, sorry, this energy to this energy, just the energy for vaporization, okay?
Delta T equals 0.
So, no, yeah, delta T is equal to 0. I'm not trying to also raise its temperature. I just want to know how much my energy went into vaporizing this stuff, okay? So I say, all right, the mass is equal to 0.2000 kilograms. All right, all good. LVW is equal to 2.3 times 10 to the power of 6 joules per kilogram. And when I go to figure out the energy, evaporization for this water is equal to mass times LVW. Oh, look at that. I wrote it as mass before LVW. Sorry about that. People like to write the L first. My mistake. That's bad form on my part. 2.3 times 10 to the power of 6 joules per kilogram. There, I'll correct myself and put the LV first when I sub it in. Times the mass is 0.2000 kilograms. 460,000 joules. Wow. When I measure the amount of energy it takes to vaporize a glass of water compared to how much energy it takes for me to climb the stairs, it gives some respect to this, right? Like, there's a lot of energy here. And I want to make sure that we get that there's a lot of energy used in heating things. This is a big thing to keep our heads on. It also explains why it takes so much energy to heat our homes. Heating our homes takes a lot of energy, right? Like anything thermal takes a lot of energy. Recently, I read a thing saying that the ovens that bake the bread around our province take more energy than the auto plants. I got to do some more reading to see if that's true, but I'm starting to wonder, like maybe this is true. Maybe we're putting more energy into baking bread. And maybe that's not so much of a slight against the bread factories as it is like a gold star for the fact that our engineering in our auto plants is getting more and more efficient. Maybe that's the thing to keep in perspective here, right? But heat really does take a lot of energy. I want to take a look at this device because this is the kind of device that shows up commonly in our homes. And it really does show this idea of the energy graph that we're talking about. Now, I haven't drawn the energy graph.